Well, greetings everybody. I'm pleased to be making this video to solve this problem which I've taken directly from my math lab. But it's a lot more than that, meaning it's more than me just showing you how to do this problem on my math lab. Okay, what I'll address here is something very fundamental about the derivative, and here's why I think it's so important and so fundamental. Calculus is a tool. It's a tool that scientists and engineers use to solve problems. But think about it. Think of all the math you've learned. You've learned some algebra, and sometimes that's the right tool to solve a problem. There's geometry and trigonometry, and sometimes those are the right tools to solve problems. There's statistics and so on. There's all these different branches of math, and I just see it as they're different tools to solve different kinds of problems. And what would be important as you go forward and you do something in mathematical sciences or engineering is to see a problem and recognize what the right tool is. Now, sometimes calculus is the right tool to solve a problem, but I think in order to know that it's a right tool for a new situation that you see, you'll need to understand what it is. Okay, so like here, this question is about derivatives, and it's about a certain aspect of derivatives that, if you understand, will help you realize when calculus or derivatives is the right tool to solve a problem. So you could say this question is conceptual. All right, it's about understanding something about the derivative more than doing any kind of calculations. Okay, so that's my preface to what I'm about to show you. Now, even before I show you this problem, I want you to think about something. Okay, and here is what I want you to think about. Okay, so you thinking about this, I think, will get your mind in the right preparedness to understand what I'm about to show you. So suppose I have this triangle, and it's a right triangle, and this side is fixed at 3 centimeters, and then we have this angle here and the hypotenuse here, and these two things can change. Okay, so you might imagine that if the angle got bigger or smaller, but this side stayed fixed, it would cause this other side y to change. Okay, they're going to change together somehow. Now, in order for that to happen, like if this side was going to stay fixed and this angle was going to change, like this point would have to scoot that way. That would make the angle smaller and the hypotenuse bigger. Okay, so just think about that. Think about all the ways that if you had this triangle and you kept this side fixed, that these two things could change together. If the angle changed, it would force the hypotenuse to change also, and vice versa. So just think about that. All right, use your imagination. If you want to, you could even, like me, you could get a protractor and draw some sketches of the triangles, start changing things and see what happens. Think about it like this. Like if theta changes, y will also have to change, right? Do you understand that? Do you see how they would change together? Do you see how change in the angle causes change in the hypotenuse? Okay, now we're interested in that in calculus. So we might see all kinds of situations where change in one aspect causes change in some other aspect, like cause and effect. And will change in one part cause change in another part that's a little bit or a lot? You know, maybe the hypotenuse is very sensitive to changes in the angle. Maybe a small change in the angle causes a big change in the hypotenuse, or maybe not. But that's the kind of thing that we wonder about when we're working with derivatives, is how does change in one thing cause change in another? Okay, so will it change a little? Will it change a lot? If the angle gets bigger, will the hypotenuse get smaller, or will it also get bigger? There's all kinds of things that we could wonder about when it comes to change in one aspect of a system causing change in another. So I just wanted you to think about that to get in the right mindset to do what we're about to do. Okay, so here's this. Let's go back to this question. Let's answer it. So we got that right triangle that I just showed you up there. You've got this angle theta. You've got this side fixed at 3 centimeters, and then you got the hypotenuse. Okay, which is true about the derivative dy over d theta. So talking about that a little bit, first of all, dy over d theta is called Leibniz notation. And there's Leibniz if you want. You can read about him if you want to. But that's another notation for the derivative. Okay? Now, you might say, why don't we just use the notation that we've already learned, y prime? You know, if we put an apostrophe next to a variable, that could represent its derivative. Okay, so why do we not just use that? What's with this new notation? Well, what we like about this notation is that it tells us the variables involved. Okay, and it gives you a way to think about what the derivative means. So dy over d theta tells me this. It tells me how a very small change in theta gives a resulting change in y. And when I get that number, I can interpret it that way. Okay? All right, so we use that notation for the derivative sometimes because it contains the information about the variables involved. Or if you just put y prime, you don't have all that. Okay? Now, this doesn't change what the derivative is. It doesn't make it different. It's just a different symbol that contains information about the variables. All right? Okay, now we use that a lot in math. Like here's something about Newton's laws of motion, and already I see a lot of the stuff that we've used in our class. Delta S over delta T. That means change in S over change in T. Okay? ds dt, there's Leibniz notation right there. All right, which roughly means it's going to tell me if I can calculate this, how change in T causes change in S. It's going to answer that question for me. Okay, this is specifically about motion. And if something's moving, as time passes, its position changes. That's what this derivative means. Delta S or ds over dt, S is position, T is time. The derivative tells me how those are changing together. And if your position changes as time passes, that's motion. Okay? So like there's a lot contained in that symbol that I might not see if I just put S prime or something like that. Okay, so let's go back to this. So that's what dy over d theta tells me. How about this? Let's answer this question by just thinking about this, that dy over d theta is going to tell me how a small change in theta causes some resulting change in y. Okay, and I see my answers like being, it will be negative, it will be positive, it will be this formula or that one. But I think it's just going to come down to whether it's positive or negative. Let me show you why. So here I've sketched out some examples. Okay, and I tried to do this as accurately as I could. I used my ruler and protractor to measure everything. And there's going to be some measurement error here, but I still think it's pretty good and it will illustrate my point. All right. So I took this arbitrarily to make theta about 40 degrees, and I measured with my protractor that this is 3 centimeters because that side is fixed, okay? And that y was about 4.7 centimeters. Now I'm curious, if I did a very small change in the angle, how would y change, okay? So what I did is I pushed this side inward a little bit. That made this angle a little bigger. Now it's 52 degrees. I kept this side fixed at 3 centimeters, and then I measured this side to be 4 centimeters. So look what happened. Here's the nature of this situation. Change in theta causes change in y like this. If theta gets bigger, it forces y to get smaller. Okay? I can see right there, like with my measurements, I could even just imagine this triangle in my head. Maybe you could do that too. So yeah, y will get smaller as theta gets larger, and that means dy over d theta will be negative. Okay? So that's how I know that it's going to be A. Now, why it's not B or D is that these formulas just don't correspond to the situation. Okay? We'll see in some other examples how that is. I'll do some calculations in addition to just figuring out is the derivative positive or negative and what does it mean. And I'll show you those in an example like this right here where we'll do the calculations. But yeah, you'll find out that if we look at that triangle, this and that is not the formula for the derivative. It can't be positive because we just looked at it like this. Dy over d theta has to be negative. Okay, so that's the thinking that's involved in this one. And like I said, I think even though it's not some kind of difficult calculation, there's no complicated formula to get the answer, it's still very important because it captures something about the derivative that we really need to understand.